In Chapter 1 of our textbook, we'll find many pictures or particle representations. In Chapter 2, we find more, and in Chapter 3, there's quite a few. In this video, let's take a little bit of time and look at how these different particle representations show us different things chemically in terms of states of matter, chemical and physical changes, ionic and molecular descriptions, and also chemical reactions. These topics are found in chapters 1, 2, 3 of our textbook, and they'll continue throughout the semester. In chapter 1, we saw that we could begin with a molecule like this O2 molecule. It could be present in different states of matter, perhaps a solid, a liquid, or a gas. Looking closely at the solid, we see an ordered pattern of one molecule next to another, next to another, next to another. In each case, we see this discrete O2 molecule, but we see an ordered pattern to it. In contrast, for the gas, it's again an O2 molecule, but now they're separated far apart from each other. This is showing an O2 molecule in different states of matter. In chapter 2, we begin to look at ionic compounds and how they form. So if we begin with a neutral sodium atom, a neutral chlorine atom, if we have a transfer of an electron, we end up with a cation and an anion. The formation of the ionic compound occurs when these cations and anions come together in this extended lattice, this three-dimensional arrangement, this alternating pattern of cations and anions. So here's a particle description of sodium chloride solid, which is an ionic compound with this alternating pattern. This idea then is applied by looking at this question for ionic compounds and molecules. Which diagram most likely represents an ionic compound, and which is a molecular one? What should we be looking for? I see very different descriptions between the figure on the left and the one on the right. Ionic compounds, like sodium chloride, have very high melting points and are usually solids. The one on the left looks like a solid. Small molecular compounds, like carbon monoxide, are usually gases. On the left, I see this alternating pattern of presumably cations and anions in a solid. And on the right, I see looks like a gas with these discrete molecules. So I'd say the one on the left best represents an ionic compound, the one on the right, a molecular one. What if we're looking at ionic compounds, including cations and anions, and we want to consider the empirical formula? This question says, the diagram represents an ionic compound in which the red spheres represent cations and the blue spheres represent anions. Which formula is consistent with the drawing? Take a moment, stop the video. What would you look for when answering this question? For me, a leading point is the red spheres represent cations and the blue ones anions. So there's a cation to anion ratio in the image of 1 to 2. For every one cation, there's 2 anions. So which formula is consistent with the drawings? In each of these, a cation is listed, followed by the anion. Sometimes the anions are polyatomic. KBr has a 1-to-1 ratio for cations and anions. We have a ratio of 2 to 1, 1 to 2, and 2 to 3. So based on the cation to anion ratio, the best answer is the calcium nitrate. 1 cation for every 2 anions. Here's an exam question that combines these ideas. It says select the particle description consistent with the solid substance. So they're all packed together as solids, and there's different choices. To answer this one, I wouldn't look at the choices. Let's first see what the different diagrams are representing. The first one looks like an ionic compound with this alternating pattern and a cation to anion ratio of 1 to 1. What does the second one represent? Also looks like an ionic compound that could be in a 1 to 2 or a 2 to 1 ratio. How do we know it's an ionic compound as a solid and not a molecular one? In 3, we see that we have molecules that are discrete, they're apart from each other. That's different than what I found in figure 2. This would be a description for a molecular solid. Remember the O2? When we had that as a solid, we had those molecules slightly separated from each other. They were still discrete and distinct. This looks like a compound with 2 different elements. That is a molecular solid. Finally, the last one, all of the particles appear to be together. All of the atoms are the same kind and stuck together as a solid. This looks like an elemental solid. Now let's return to our choices and see which one could be correct. So the first says that figure 4 could be oxygen. No, I don't think it's oxygen. I think it could be an elemental solid, maybe sodium solid, calcium solid, but I don't see distinct O2 molecules. Could 3 be sodium chloride? No, this is molecular, not ionic. Could be something like NO or CO solid, but not sodium chloride. Carbon dioxide? Carbon dioxide would be a molecular solid. This is an ionic one. Calcium nitrate, potassium oxide, those would be consistent with this description. Which brings us down to 1. Could that be magnesium oxide? It would be an ionic solid with a 1-to-1 ratio for cation to anion. That's a match for this picture. Potassium chloride, chromium nitride, those would also be examples of ionic solids with a 1-to-1 ratio. How about this one? In the figure, a mixture of 2 gaseous elements undergoes a blank and form blank. Take a second, pause the video. What do you think about this one? What are you looking for? Within my analysis, I see that the product are discrete molecules, not an ionic solid. This is also a chemical reaction. A new substance is formed. So if we look at our choices, we can begin by crossing out those that indicate an ionic solid is forming. This looks like a molecular solid. A physical change, nope, it was a chemical change. So we want to find an example where a chemical reaction is described and a molecular solid is being formed. The final point is we need to distinguish between a combination reaction and a decomposition reaction. This is a combination reaction, as we have 2 substances combining to form a new one. This question is a particle representation picture for a chemical reaction. It begins by saying the diagram represents a mixture of NO and O2 molecules in a closed container. And we have a little key to show that the black ones are the nitrogen, the open spheres are the oxygen. Which diagram shows the results after the mixture reacts as completely as possible according to a balanced chemical equation that is provided? So within our analysis here, we want to attend to 2 things. What is the correct product in the provided image, and is there a limiting reactant? So let's start with what is the correct product? What do I expect to see at the particle level? It says that NO2 molecules are being formed. NO2 is the product. Which of those are shown in the pictures and which ones are not? Here's an NO2 molecule. It's nitrogen and oxygen and oxygen. That's what an NO2 molecule is like at the particle level. That's also found in image 4, but I have some leftover NO molecules. Why would I have leftover NO molecules? Is that possible? We now have to consider what is the limiting reactant, because this is a closed container. I can't be adding or removing particles. So how do we keep track of how the reactants change their amounts leading to the products being formed? Well, we need a balanced chemical equation, and let's keep track of that with the BCA table. It tells me what I have before the reaction, how it changes, and what I have afterwards. If we look at the image, we see that we have 6 NO molecules to begin with, 2 O2 molecules, and none of the product. I'm getting those amounts just by looking at the initial image and counting up what is there. It changes by the NO going down by 4 molecules, the O2 going down by 2 molecules, and the NO2 increasing by 4. These changes are consistent with the coefficients within the balanced chemical equation. The O2 was the limiting reactant. I use up all of that and the reaction stops. So afterwards I don't have any O2 left. I'd have 2 NO molecules remaining and 4 NO2 molecules. That's what I find in image 4. The topics presented here, we're looking at different ways of looking at particle representations. Could be states of matter, chemical or physical changes, considering ionic and molecular substances, and finally chemical reactions. These are found in chapters 1 through 3, and they'll be continued and used throughout the textbook.